So question 1939, it says the 12 kilogram rod AB, it is pinned to the 40 kg disc. If the disc is given the angular velocity 100 radian per second, while the rod is held stationary and the assembly is then released. Determine the angular velocity of the rod after the disc has stopped spinning relative to the rod due to frictional resistance at the bearing B. Motion is in the horizontal plane. Neglect friction at pin A. So we are given with the mass of the rod, which is 12 kg, and mass of the disc, which is 40 kg, and the initial angular velocity of disc is 100 radian per second, and the length of pin A to pin B is 2 meters, and the radius of the disc is 0.3 meters, and we have to find the angular velocity of the rod after at the moment the disc has stopped spinning. So first we have to find the inertia of A. So pin A, so we know that the rod and the disc moves as one body, so that's why we have to find the inertia of this rod and also the disc. So we do that. So 1 by 3 mrl square plus 1 by 2 mdr square plus mdl square. So mdr square is for this disc and mdl square is because it is also attached to the rod over here. So we put in the values and we get the inertia at A, which is 177.8 kg meter square, which is the rod which is attached to the disc. And for B we only do it for the disc, and which is 1 by 2 mdr square, and we get 1.8 kgm square. So as you know that this is conservation of angular momentum because there's only movement in angular direction. First the disc, when the rod is stationary, and when the disc stops and the rod is moving, it's also moving in the angular direction. So that's why. So at the state 1 it is the rod is stationary, and IB, which is the disc, which is multiplied with the angular velocity of the disc, which is 100, is equal to IA, which is the whole, the rod and the disc, and we have to find the angular velocity of the rod, which is moving in the angular direction, and we know that the disc has stopped spinning, so we don't include that, and we put in the values 1.8 multiplied by 100, which is 180, and we know that 177.8 is the inertia at A, and we have to find the rod angular velocity, which is 1.01 radian per second, and it is after the disc has stopped spinning.